Apologies. Yes, let's start the recording. Thank you, Caroli. Such a pleasure today to introduce our Climate Salon speaker, Zeke Hausfather. Perhaps the signature of having arrived in your field is having your hostess go off and ask Claude Sonnet to write an introduction for your talk. And Claude says that Zeke Hausfather has established himself as one of climate science's most influential voices, bringing rigorous research, bridging rigorous research with great access to public communications. So that's the theme I think we're going to hear today. So Zeke went to Grinnell College, the Free University of Amsterdam, Yale, 2 masters there in climate economics, and then a PhD in climate data analysis from UC Berkeley. So he's really seen both sides of climate analysis, the academic side and the business side. He's worked with the Breakthrough Institute and was the senior climate analyst at Project Drawdown. And these days he works for a company called Stripe, which supplies a financial infrastructure, as I understand it, for aspiring new companies. And when I first met Zeke, I asked myself, why would somebody with his background be working for this company? And the answer is that these new companies want access to climate technology. So he's the resident climate expert at Stripe. And I'll tell you, his knowledge of emerging mitigating technologies is encyclopedic. We've been subjecting him to an arsenal, barrage of all kinds of questions. So we should also note that he has enormous standing just in the world of climate expertise. He's one of the lead authors on the upcoming IPCC report. He's written very influential papers with over 1,000 citations in the literature on various aspects of climate science. And I'll tell you that his Substack, called the Climate Brink, is just an incredible resource to know. He anticipates every question you have. You can go there and find a report on it. So with great pleasure, I hand the forum over to Zeke for his talk today.
Thank you so much, and thanks for having me, everyone. So I'm going to give a talk covering a number of different areas of interest in climate science recently. I sort of titled it, broadly speaking, Progress and Peril in a Rapidly Warming World, which is a little dramatic and vague. But the things I want to touch on are sort of where we are right now in the climate system. Is global warming accelerating? If so, why? What can explain some of the recent anomalous global temperatures? And then how does this feed into the broader trajectory of where we're headed? What level of warming are we likely to see by the end of the century? How has that changed over time? And what might we as a society be able to do to change that further? So I want to save lots of time for questions at the end. So as I'm talking, if you think of something, jot it down. If you do have a clarifying question about something that you don't understand that I'm showing, feel free to interrupt then. But I prefer the sort of broader topical discussion to be after. So with that, let's get going. As an aside, this background picture is an artistic representation of daily global absolute temperatures from EFI, the reanalysis product. So blue is cooler, red is warmer. There's actually a daily temperature cycle because the northern hemisphere is more land. You end up with hotter absolute global temperatures in the summer, northern hemispheric summer, compared to the southern hemispheric summer. And you can see the sort of red area expanding as the world warms. I just thought it was a nice version of sort of ad hoc climate stripes with a bit more data in it. But let's start out. So to review a little bit of where we are today, I think, and people in the audience here might know this, but a lot of people, when they think about climate change, don't quite realize the scale at which we're talking about and the scale of the perturbations which we're talking about. So since the Industrial Revolution, humanity has emitted about 2.75 trillion tons of carbon dioxide. About 2/3 of this is from fossil fuel emissions, about a third is from land use change. Now, a trillion tons or 2.7 trillion tons, it's kind of an abstract number. Most people don't actually know what a trillion tons means. And to put that in perspective, the entire dry weight of the biosphere is about 1.1 trillion tons. So everything, living thing on Earth, excluding its water content, is roughly that. The entire weight of all human-built materials, the pyramids, roads, cars, bridges, homes, everything humans have ever built is about 1.2 trillion tons. So we've put more CO2 into the atmosphere than the combined weight of the biosphere, excluding water, and everything humans have ever built. And that's a lot. That's an enormous amount. And to think that would not be causing changes on a planetary scale would be a little naive, given the scope of what humans have done. And that's had a very massive effect on the composition of our atmosphere. So this is a figure that my colleague at Berkeley with Robert Rohde made that shows atmospheric CO2 concentrations over the last 10,000 years, a combination of ice core measurements from bubbles in ice, mostly in Antarctica and some in Greenland over time, up through the modern period and the start of Roger Rebel taking measurements at the Mauna Loa station of atmospheric CO2 concentrations. And we can see that, over the last 8,000 years and 10,000 years and much before that, atmospheric CO2 is around 260 to 280 parts per million. Since human emissions took off, in that previous graph I showed, it's really spiked up. We're a bit above 420 parts per million today. And that's roughly the highest level of CO2 we've seen for at least the last 3 to 5 million years, potentially even further back, given the uncertainty in CO2 proxies. During the ice ages, it fluctuates between about 180 to 280 parts per million. But we haven't seen any periods, at least in, since the ice ages began, of CO2 concentrations anywhere near this. And so that increase in atmospheric CO2, along with other greenhouse gases, has had a significant effect on global surface temperatures. So this is a figure I made last week that compares the latest data through 2025 from the 8 different groups now that produce global surface temperature records. That includes NASA, the GIST group there, the UK Met Office, and the University of East Anglia, NOAA, Berkeley Earth, the record I helped put together, Copernicus, which is the European reanalysis effort, the Japanese reanalysis effort, DCENT, which is a new product out of Harvard, and China MST, which is a new Chinese data set that came out this past year. They all largely agree. We've seen about 1.4 degrees warming since pre-industrial. There are some differences in the early part of the record when we have fewer measurements, and how you fill in the gaps between those measurements matters a little bit more. But at the end of the day, we see a lot of agreement. There's not much uncertainty in how much the world has actually warmed. And it is pretty significant. And this is bringing us to levels of global surface temperature that are largely unprecedented in at least the last 120,000 years since the Eemian, which is the last interglacial period. Potentially even above where we were in the last interglacial period, but it's hard to know with confidence yet. And this increase in global temperatures has been fairly rapid relative to what we've seen at least since the end of the last ice age. So this is the past 2,000 years of global temperatures in the middle here. Observations of the black bit here. This is a little out of date. It should be close to 1.4 now. And then the blue line back there is a reconstruction of global proxy records as part of the Pages 2K project, which is a big community effort by the paleoclimate community to create a centralized database of climate proxies of things like tree rings, ice cores, coral sediments, all the different ways that you can use indirect measurements to estimate global temperatures before we had thermometers. There is some uncertainty here, and actually this record probably slightly understates the uncertainty. We're going to probably ratchet it up a little bit in the version we use in the next IPCC report. But anyway, you look at it, what we're seeing today is well outside of what we've seen in the last 2,000 years and likely outside of what we've seen in the last 120,000 years. Similarly, we're also seeing sea levels rising to levels that are unprecedented, at least the last 2,000 years. There are probably parts of the early Holocene where we may have had sea levels higher than today, but that occurred gradually over very long periods of time, and certainly the rate of change is quite unprecedented. Now, previously that was showing global average numbers. None of us live in the global average. The places we are actually living, land, are warming much faster than the global average, which is 70% ocean. So if we look at land temperatures, which is in red here from Berkeley Earth, the world is warmed by about 2 degrees centigrade. And again, apologies for using centigrade for folks here are not, used to that. You can roughly double it and subtract a tiny bit to get Fahrenheit. So think like 3.5 degrees Fahrenheit warming over land. whereas the oceans have been warming considerably slower, with about 1 degree centigrade warming to date. And that's largely because a huge portion of the heat that's being trapped by greenhouse gases is going into the oceans, heating the ocean from the surface down. And so while the surface oceans have warmed about 1 degree C, the deep oceans have warmed, maybe a tenth or less than a tenth of a degree C. That's actually a good thing. If we didn't have the oceans, the whole planet would be closer to 2 degrees warming today. But because we have the oceans, it buffers the rate of warming that the surface experiences. And so it buys us a bit of time before the worst impacts of the sort of effects of current atmospheric CO2 concentrations are seen in the climate system. But we should be thankful for the oceans. And speaking of the oceans, that heat, 90+% of all the heat trapped by greenhouse gases is going into the oceans. The atmosphere doesn't hold much heat. Some heat goes into the ground, some heat goes into melting snow and ice, but most of it, 93%, I think is roughly our best estimate, is going into the ocean. A lot of that is going into the top 700 meters of the ocean. So this is showing ocean heat content changes since 1950 based on the Institute for Atmospheric Physics record. There's a couple different ocean heat content estimates. They vary actually a bit more than surface temperatures because of bigger uncertainties earlier in the record. But they all show a similar increase in the modern period. And here we're seeing about 2/3 of the heat accumulate in the top 700 meters of the ocean, about a third of the heat accumulate in the lower parts between 700 and 2,000 meters. There actually are published estimates now of the deeper ocean. It's a pretty small wedge, in part just because the ocean overturning and heat diffusion is a very slow process. The units in this chart are zettajoules, billion and trillion joules, which again is one of these mind-numbingly large numbers. To put in perspective, the increase just in the last year, that last little increment of that chart, was about 26 zettajoules. And an increase in 26 zettajoules in the last year, to put in perspective, is roughly 36 times the energy content of all human energy use last year. So if you look at global primary energy use and you multiply that by 36, that's how much energy accumulated in the oceans in just the last year. So big number. Some people like to put it in atomic bombs per second. I find that kind of equally useless.
Yeah.
They're very dramatic. So I like to express ocean heat content as a multiplier of human energy use. And it also goes to show just how much more heat the emissions from our energy use traps than the actual heat content of those fuels themselves, which is startling. Ken Caldera and colleagues actually wrote a paper on this 10 years ago or so, where they found that there's roughly 1,000 times more heat trapped by a ton of coal than the energy you get from burning it over its atmospheric lifetime, which is a pretty startling number. And as a general rule, if you think of equality in climate science, Ken probably wrote a paper about it 10 years ago. It's a little annoying. So we've long known that CO2 is a greenhouse gas. This is not a new thing. This is not new science. Some of the earliest work done on the radiative properties of the atmosphere was done by folks like Eunice Foote, John Tyndall, Svante Arrhenius, who came up with the first estimate of how sensitive the climate is to our emissions back in 1896. And we increasingly can directly measure what this is doing to temperatures on the surface. It's not just climate models that tell us that CO2 is causing climate change. We can actually point instruments up and look at the forcing directly coming from CO2, how that's changing over time, how it tracks CO2 concentration. So this is some excellent work that Dan Feldman over at Lawrence Berkeley Labs did back in 2015, where they had a 10-year program measuring downward fluxes of forcing and CO2 concentrations at sites in the southern Great Plains and the North Slope of Alaska. And you can see this very strong relationship between the atmospheric CO2 concentration, which has a strong annual cycle associated with vegetation primarily, and ocean temperatures, and the radiative forcing from that CO2, which is being directly measured, which is pretty much in lockstep with what we're seeing in terms of CO2 concentrations. And those are more or less directly in line with what models would expect the radiative forcing to be. So we can directly see it. Now, I've been talking a lot about CO2, and CO2 is a really important part of the equation, but it's not the only. Humans have affected the climate in a number of different ways. And so this plot, based on some modeling I did using the FAIR climate model, shows a breakdown of each different element of human influence and natural influence of the climate system in isolation. So if we just had greenhouse gases, CO2, methane, nitrous oxide, our best estimate of warming since 1750, or since 1850, sorry, would be about a bit more than we've actually experienced. We have warmed about 1.6 degrees C just from greenhouse gases. if we look just at other anthropogenic factors like tropospheric ozone, stratospheric water vapor, albedo changes on the surface, the world that are not feedbacks but are forcings due to land use change, we would have had about 0.3 degrees warming, 0.35. If we look just at natural factors, volcanoes, solar output changes, it's a very small amount. The other really interesting part of this graph, though, is the blue line there. And the blue line represents aerosols. Now, aerosols is a pretty big group of things that represents small particulates in the atmosphere. But the biggest part of that is sulfur dioxide. Human emissions of sulfur dioxide have been a strong cooling factor, but a very uncertain one. So our best estimate is that sulfur dioxide emissions have cooled the planet about 0.5 degrees C, a little bit more than that probably, since pre-industrial. But with error bars that range from about 0.3 degrees C to 1.2 degrees C. So anywhere in that big range could be the effects of aerosols. And those have been changing as well over time. I'll talk about this in more in depth later, but you can see that curve of aerosol forcing or aerosol warming or cooling, I guess, technically, peaks around 2000, 2005. And in the last 15 years, it's diminishing as emissions have declined. So if you add all these different factors together, you get that yellow line, which is the model's best estimate of actual warming. And then the dashed line is the observations we have to find a system, which match up generally pretty well. There's some excursions around World War II, or in the early 1900s that are debatable, and some uncertainty in the observational records there as well. But broadly speaking, the amount of warming that we've experienced is more or less in line with what models expect, given the combination of all these different factors that are affecting the climate. Now, we've also seen an uptick in the rate of warming in recent years. So the last 3 years, 2023, 2024, and 2025, have been the warmest years on record, and by a fairly big margin. This actually doesn't include 2025, but if you included it, it would be right about there, roughly equal to 2023. And if you look at the last 15 years, so the red line here is showing the trend from 2009 to 2023. I forgot to update this to 2024 for the trends, but it would be very similar to that. You see a distinctly faster rate of warming over that period than we've seen since the 1970s. So since 1970, we had a rate of warming of about 0.2 C per decade that was pretty consistent. The last 15 years is actually closer to 0.4 C. Now, some of that is attributable to internal variability in the climate system. We had a strong El Nino event in 2024, which pushed things up a little bit. We had a modest La Nina event in 2011, 2012, pushed things down a little bit. Other estimates of the rate of warming in recent years are a little lower that try to account for only human factors. So we published a paper last year that was led by Piers Foster in the UK, where we used a bunch of different approaches to settle on a number of about 0.27 C per decade warming that we've experienced in recent years. But that's still an increase of about 30% compared to the rate of warming that we've seen since 1970. So this might exaggerate the scale a little bit because of internal variability, but there does seem to be a pretty clear signal emerging that the rate of warming has increased compared to what we've seen historically. That being said, an increase in the rate of warming is somewhat in line with climate model expectations. So a lot of stuff going on in this plot, but the upper left is the same observations that I was showing earlier. Every dot is a year. The dashed line is a linear trend, and then just extending that linear trend out through 2050. So given the rate of warming since 1970, that's roughly where we expect temperatures to be in 2050. The upper right is the sort of headline warming projection in the most recent IPCC report, using a scenario that's most analogous to current policies, which is called SSP 4.5. And in that scenario, you see the rate of warming is notably higher than you get by just extending that 0.2 C per decade rate out through 2050. It's about 24% higher or so. Similarly, if you looked at the latest generation of climate models, the CMIP6 models, you get warming in the future that's significantly higher than a linear extrapolation. This ends up being about 40% faster warming, or sorry, 30% faster warming. I'd have to double check that than the historical rate. I think it's 40 actually. And then James Hansen came out with an estimate in a paper he published last year, or 2 years ago, where he said that the rate of warming would increase by 50 to 100%, which is the shaded intervals here. Not quite 50, sorry, 25 to 50%. I'm forgetting the exact numbers, but Hansen came up with a projection of an acceleration of the rate of future warming, which is shown there as well. And so in all these cases, we see an expectation of an acceleration of warming. But the question then becomes, well, what is going on here? Why do models expect acceleration of warming? Why are we observing acceleration of warming? What are the different drivers here? So my hypothesis, and I've written a bit about this, both in the peer-reviewed literature and some of my own sort of writings, is that most of the apparent acceleration rate of warming is attributable to both continued increases in greenhouse gas emissions, but particularly reductions in aerosol forcing on top of those continued increases in emissions. So continuing increases in emissions would keep warming roughly at the rate we've seen since 1970, but to get that increase in the rate of warming on top of this historical rate, you can add reductions in aerosols. So this plot shows sulfur dioxide emissions, which again is the bulk of aerosol cooling, by country over time. And there's a couple things to point out here. You can see in the US and Europe, Clean Air Acts introduced in the 1970s and 1980s, dramatically reducing these numbers, as well as things like the acid rain mitigation rules introduced in the 1990s. And so now sulfur dioxide emissions in the US and Europe are vanishingly small. During that period, China's emissions increased dramatically, peaking around 2007, 2008, which is also when they hosted the Olympics, where famously the air in Beijing looked like pea soup. And people were complaining publicly. Since then, that line has crashed about 75% down to a much smaller value. And so China has really, mandated the use of scrubbers in coal plants and taken other measures to dramatically reduce its sulfur emissions. India has significantly increased its sulfur emissions. Russia's have declined a bit. The rest of the world has declined a little bit. And then there's this very interesting bar at the bottom, which is shipping and aviation, where there was a new set of regulations put in place in 2020 that required an 80% reduction in the sulfur content of shipping fuels. And so that led to a pretty sharp drop in 2020. There's also a sharp drop associated with COVID that shows up in some of these lines as well. But most of that drop has been a sustained reduction associated with a transition to low sulfur shipping fuels globally. That was mandated by the International Maritime Organization. So we can break this down into three of those separate categories. So the light blue line at the bottom is shipping's SO2 emissions. This is particularly shipping excluding aviation. And so you can see that drop. The dark blue line is Chinese emissions. Again, a pretty big drop. And then the gray is all the rest of the big emissions, which dropped pretty significantly, through 2008 or so, and have declined a little bit more modestly since then. So to zoom in on shipping for a little bit, there are reasons to believe that the reduction in shipping SO2 will be particularly efficacious in its climate impact. So sulfur, it has two main ways that it cools the planet. One is that it's directly reflective. It scatters incoming sunlight back to space. That's called the direct aerosol or aerosol direct effect. But there's also an aerosol indirect effect where these little particulates in the atmosphere of sulfur or sulfate can serve as cloud condensation nuclei. So you don't generally have cloudy behavior if the air is very, very clean. You need a certain amount of background concentrations of aerosols in order for clouds to form. Some of this comes naturally from sea salt, from dust, from various other factors. You don't just need humans. But if humans are putting lots of aerosols into the atmosphere, it can also increase cloud formation, particularly of low clouds that are very reflective. So you end up with a fair amount of cloudiness coming from these sulfur emissions. Over the oceans, because there's relatively low background concentrations of sulfur dioxide, you're going to generally have a bigger effect for changes in emissions there than you'd have over, say, China, where the background concentration is very high because you have saturation dynamics, both for direct and particularly for indirect effects. So at some point, you have enough condensation nuclei up there. Adding more is not going to change things that much. So you get less changing clouds per unit of sulfur. And so places like China are pretty saturated. Places like the oceans are a lot less. And so when you see big changes over shipping lanes, so the upper left here is shipping SO2 emissions historically before the rule change. You can get some pretty big changes over these regions. That being said, the ocean is not completely pristine. There is natural sulfur emissions called dimethyl sulfite that come from cyanobacteria. And those lead to some background concentrations that already encourage things like cloud formation. So it's not quite the same as having a completely pure air environment in terms of its effects. But we expect it to be larger than overland. So there have been a number of estimates published in the last 2 years on this topic, because it's garnered a lot of interest with the scientific community. This is 8 different studies published between 2024 and 2025 that looked at the radiative forcing effect of, excuse me, of the shipping rules. So specifically, how big a change in forcing was there as a result of this 80% reduction in shipping sulfur emissions? Generally, these found an estimate of somewhere between about 0.1 watts per meter squared globally on average to about 0.15. They're reasonably clustered. There's some variation. These are primarily using different Earth system models to plug in the regional factors or the regional changes in emissions and look at the effects of that. And then James Hansen published an estimate that's a little bit of an outlier, where he argues that this factor alone is responsible for half a watt per meter squared of global radiative forcing, which would be a very, very big effect. Now, we can translate these radiative forcing estimates into a global surface temperature response. And to do that, I took all of them, every single one of these different estimates. And for each of them, I ran an 850 member ensemble of the fair climate model, calibrated to match the distribution of climate sensitivity and carbon cycle feedback estimates in the AR6, essentially to calibrate it to match the range of assumptions in the most recent IPCC report for all those different factors. And so you get if you sort of take 850 ensemble members for each of those different 8 estimates, you get a very big cloud of results. And this shows the 5th and 95th percentile of that, as well as the median estimate for all those different runs. The high one is very much dominated by Hansen's half watt per meter squared, which would give you something more like, 0.15 C warming, or even up to 0.2 C warming just from shipping. Most of the other estimates that are around 0.1 to 0.15 watts per meter squared give you something closer to 0.05 C temperature change, but it's pretty uncertain. Similarly, we can run an analysis like that for China, and there's 75% reduction in SO2 emissions. And if we do that, we get a central estimate for China of about 0.07 C warming associated with Chinese aerosol reductions globally. Again, the regional effects are much bigger than that. You get much more warming over China specifically, but the global average impact of those aerosol reductions is about 0.07 C. This turns out is also identical to the estimate that Bjorn Sunset gets in a new paper using 3 different Earth system models to do the same analysis of Chinese aerosol reductions. So there does seem to be some agreement in the literature, at least on the Chinese number. And then if we try to add these all together using our best estimates, and again, the error bars are wide, so take this with a grain of salt. You can look at the effect of international shipping, which really picks up after 2020. You can look at the effect of Chinese emission reductions, and you can look at the effect of other global emission reductions of sulfate aerosols. And the combination of all those gets you about, by 2030, about 0.15 C additional warming. And by 2024 or so, about 0.13 C or 0.12 C additional warming. And to put that in perspective, that's about a quarter of all the global warming the world has experienced since 2007 or so, when aerosol emission reductions started happening in earnest. So it's a pretty big change that we're seeing associated with these aerosol reductions. And if you then look to see how that impacts the rate of warming, so this chart shows climate model output of the rate of warming from human emissions in each decade. So each of these points is a decade period. So 1905 to 1914, 1920 to 1929, et cetera. So it's decade periods incrementing by a year. And then this is all the different contributors to the rate of warming during that decade. It's the amount of cooling associated with increasing aerosol emissions, the amount of warming associated with increase in CO2 emissions, or increasing the amount of warming associated with CO2 emissions, the amount of warming associated with methane, other greenhouse gases, primarily nitrous oxide, and halocarbon emissions. So CFCs are also in there. And then other anthropogenic factors, tropospheric ozone, land albedo change associated with anthropogenic activity, that sort of thing. And what's interesting is if you look at just the sum of greenhouse gases and other anthropogenic forcings, well, specifically, if you look at everything but aerosols, you end up with about 0.2 C warming expected, from 1970 roughly onward. And here what's happening is you get more and more warming from CO2 as CO2 emissions are increasing. But at the same time, you're actually getting a little bit less warming from other greenhouse gases, and that's largely associated with reduction in chlorofluorocarbon and other halocarbon emissions from the Montreal Protocol, because those themselves are actually quite strong greenhouse gases. And again, this is the rate of warming, so it's the derivative of the actual warming. So don't interpret this as the temperature over time, interpret this as the change in temperature every decade. So now looking at aerosols, what's interesting is aerosols went from contributing to a lower rate of warming in each decade, but in the last decade, contributing to a higher rate of warming. And again, that's because we are emitting less aerosols and therefore less of the greenhouse gas warming is being masked. So if we look at the net warming rate, we can see that it's roughly 0.27 C per decade, which is roughly our best estimate from the Foster et al. Paper of the current anthropogenic warming rate. And if we didn't have this aerosol switch, if aerosols stayed unchanged, the warming from all the other factors would still be roughly constant at about 0.2 C per decade. So at least in this analysis, pretty much all of the acceleration in the decadal rate of warming is coming from this reduction in aerosol emissions. Now, that being said, this is one analysis. There's another paper that's in review right now by Drew Schindel and colleagues that argues that only 2/3 of the acceleration is attributable to aerosols and a third isn't. The error bars on all this are very big. Yeah.
I think it's a clarifying question. Here's your way, I understood what you're saying, to fit the aerosols, persist for example, 1 year.
It's more in the order of a couple of weeks.
Okay.
Yeah, it's very, so we're talking here about tropospheric aerosols in the lower atmosphere.
Don't worry about persist.
Yeah, so there's no accumulation. It's purely a rate of emission. It's a function of the rate of
I
emissions.
think there's a background rate. Cyanobacteria is up that.
Dust, sea salt, there's sort of a background concentration in that, but that's not changing. This is just looking at the changes over time. Yeah. But it's a good question. And if you have aerosols in the upper atmosphere, they do last for a couple of years. That gets a little bit more complicated. So like big volcanic eruptions, Pinatubo, for example, will put aerosols in the stratosphere, and there they can have a more lingering effect. But in the troposphere, very short life. It precipitates out pretty quickly with rain. Okay. So on top of that, the past 3 years were quite anomalously warm. So this shows every year color coded by what period of time it occurred in. And you can see, you know, up through the 2020s, and then suddenly 2023, you know, gets really hot. September 2023 here is a whole half a degree higher, higher than the previous September. At the time, I called it gobsmackingly Venice, which found a bit of a life of its own. And then 2024, you know, was quite warm and even exceeded 2023 for a good chunk of the year. 2025 has been a little bit cooler, but still quite anomalous and quite a bit above any year we've seen before. And so there is a question not only of is global warming accelerating, but specifically why these 3 years were so bad. And those questions are related, but they're also a little bit second. You know, acceleration tells us the longer term change over decadal timescales. Individual years are going to be influenced by a number of different factors. And so I worked with Gavin Schmidt at NASA to do an analysis. We held a session at the AGU last year, or the year before last, actually now, on drivers of anomalous recent warmth. And we got a huge amount of papers by the community. And we tried to do a bit of a synthesis of like, specifically for 2023 and 2024, what were the drivers of that anomalous warmth? So we started by figuring out what was the anomaly? Like how much warmer was it than we expected? Which is this red bar here, the actual warmth anomaly compared to, you know, the longer term trend plus some acceleration. Then we looked at all the different factors that were in the literature that people had suggested to try to explain why that anomalous warmth had occurred. So one big one is El Nino and background variability. El Nino, of course, a strong El Nino event can lead to higher global temperatures, usually in the year after El Nino peaks, with a very strong event contributing up to 0.2 C additional warmth globally to global mean surface temperatures. Yeah.
What's the hatching?
Uncertainty.
Uh-huh.
That's the error bars. Right. It's just a fancy way of doing the whiskers.
Okay.
So El Nino can be a big factor, and we know there was a strong El Nino event, not super strong, but strong in 2023 that really manifested, or we'd expect to manifest in global temperatures in 2024. So we see this pattern regularly with El Nino, where the year after it develops is the year that ends up being really warm. So an El Nino developed in 1997 and made 1998 super warm. An El Nino developed in 2015 and made 2016 super warm. And so when an El Nino developed in 2023, we expected 2024 would be super warm. It was, but, and I'll get to in a second, there's some reasons to think that this El Nino also might have contributed more warmth to 2023 than we'd expect based on the historic relationship between ENSO conditions or El Nino conditions and surface temperatures. Shipping SO2, we covered a little bit earlier. Again, the central estimate is relatively modest across all those, but the error bars are quite big, with Hanson's estimate very much dominating the top up there. Chinese SO2 changes have had a really big effect over a 15-year period, but because this is just looking at the changes relative to 2022, the impact of Chinese SO2 declines is much more modest, or relative to 2020, I should say. There was an unusual volcanic eruption in Tonga called the Hunga Tonga. I'm probably going to mispronounce the other two H's, so I'm not going to try, but we call it the HTHH volcano. And why it was unusual is that it erupted underwater, but it was an incredibly explosive eruption. And so it put about 150 million metric tons of water vapor into the stratosphere. And water vapor in the stratosphere is a fairly strong greenhouse gas, has a bigger impact in the upper atmosphere, but can also have effects on the surface. And at the same time, this volcano put the largest amount of aerosol loading into the stratosphere since Pinatubo. So it didn't have nearly as much sulfur as Pinatubo, but it still had a decent amount of sulfur dioxide and other reflective particulates that it put up into the stratosphere. There was a recent paper, a recent synthesis report by the World Meteorological Organization on this volcano. And they found that you essentially have two countervailing forces. You have warming on the surface from stratospheric water vapor. You have cooling on the surface from stratospheric aerosols, but they have different lifetimes. The aerosols have a shorter lifetime in the stratosphere than the water vapor. And so our best estimate is a small net cooling effect of the volcano in the first 2 years after it erupted in 2023 and 2024, transitioning to a slight warming effect in 2025 and 2026. But again, the magnitude is quite small. I think the central estimate in their modeling was about 0.3 of a degree C surface warming and surface cooling, which is in line with what we showed in this figure.
What about clouds and albedo increasing because of the water vapor?
So we're talking about it in the stratosphere.
Okay,
So the clouds don't really form.
okay.
So high part of the atmosphere. If it were in the lower atmosphere where clouds do form, it would be very short-lived. Water vapor in the stratosphere, just like aerosols, lasts days to weeks before it falls out. So it wouldn't have had much of a persistent effect. The solar cycle, solar cycle 25, the one we're currently in today, was unusually strong. So considerably stronger than the previous solar cycles in the previous two solar cycles. And so between trough and peak, solar cycle, 11-year solar cycle changes can contribute up to about 0.1 C fluctuation in global temperatures. And so the switch between, 2022 and 2023 and 2024 solar cycle activity had some effect on temperatures. And so then if you combine all these different things, you can explain about half of the anomalous temperatures in 2023, and you can explain pretty much all the anomalous temperatures in 2024. Which does leave this interesting gap in 2023. Now, there's been a couple papers that have suggested that the 2023 El Nino was weird in that it led to heat in the climate system earlier than you'd normally expect in an El Nino event. The reason for that is that prior to 2023, there was a very extended triple dip La Nina event. So between the end of 2020 and the start of 2023, there's mostly uninterrupted La Nina conditions. It sort of was in La Nina, it kind of came out and then went back, and then kind of came out and then went back. And so there's some evidence in the historical record that when you have very extended El Nino conditions, very extended La Nina conditions followed by an El Nino event, you can lead to a much more rapid spike in temperatures than you normally have for El Nino. There's not great analogs there. It's a little hand wavy, but I do think personally, at least, El Nino behaving weird is the leading explanation for that gap for 2023. But more work to do on that. Okay, so switching gears a little bit, we've talked a bit about why warming is accelerating, why the last few years have been weird. Let's talk a bit about where we're headed right now and how that might change. So today, global temperatures, as I mentioned, have warmed by about 1.4 degrees centigrade. If we look into the future, we'd expect this warming to continue. So this is showing that scenario I mentioned earlier, the SSP2 4.5 scenario, which is roughly analogous to a world where global emissions plateau, global emissions of CO2 and greenhouse gases plateau before falling by the end of the century by about half. Aerosols decline as clean air regulations come into place. Hopefully we'll cut emissions more than half by the end of the century. You could look at worse scenarios, but this one is roughly in line with literature on current policies. And every line right there is a different climate model from the CMIP6 ensemble with a smooth to remove year-to-year variability. And so this is one way. There are many different ways to look at when the world might cross different climate thresholds. This is roughly equivalent to an approach that Richard Betts and colleagues used of combining historical observations with future climate model projections. But at least in this sort of estimate, you end up crossing 1.5 degrees, somewhere between the late 2020s, so 2028 to the early 2030s, around 2032, with some models a little more on the extremes. And you end up crossing 2 degrees sometime in the mid 2040s to the early 2060s. That's not a great scenario to be in. I for one don't want to end up in a world close to 3 degrees by the end of the century. But that does seem to be roughly where we're headed today. And if we actually did want to limit warming to 1.5 degrees, the math on it is increasingly brutal. So if you want to stop the world from passing 1.5 degrees today, and this is actually 2 years out of date, so it'd be a lot worse right now, there's a vanishingly small carbon budget. So that black line is as of 2023. If you wanted to prevent the world from exceeding 1.5 degrees warming, you'd have to get all global emissions to zero by about 2032. And every year you delay, so again, this is 2024, 2025, that curve gets steeper and steeper until by 2028 or so, it's a straight line down. You've pretty much passed it. This is why pretty much all scenarios that limit the world to 1.5 degrees by the end of the century have some degree of overshoot on the way there. You end up getting to 1.6, 1.7, 1.8 by mid-century, and then spend trillions of dollars to suck mind-numbingly large amounts of carbon out of the atmosphere to bring temperatures back down. Doesn't violate the laws of physics, but it would be difficult to see how it happens in reality. Now, if we look at a world of 2 degrees, or below 2 degrees here, so this is actually a 66% chance of avoiding 2 degree warming, sort of a SSP 1 2.6 style scenario, or RCP 2.6 for folks who know the scenario names. You end up with a bigger carbon budget. Again, it's a pretty steep slope, and every year we delay, it gets steeper and steeper. If we had started back in 2000, it would be a gradual walk through the park. Today, it's more of a double black diamond, or at least a black diamond. And the further you wait, the more steep it gets. I took calling this the ski slope thought because it's sort of a different difficulties. But again, you could imagine a world getting to zero emissions by 2070, potentially without having to rely on as much net negative emissions. It's still going to be hard. And again, every year we delay, that curve has to get steeper because it's the integral of it's the area under the curve that matters for our emissions and the warming you result. So that's what would need to happen. Where are we today in terms of emissions? Well, there's a little bit of good news. We were increasing emissions very rapidly in the 2000s and early 2010s. It was growing at 3% a year. Since 2012 or so, it's more or less plateaued, technically growing at about 0.8% per year, maybe a little bit less, but significantly lower rate than we've seen previously. This plot shows the last 5 global carbon budgets. The global carbon budget is published by the Global Carbon Project, which is a big consortium of scientists who look at all the emissions data and the sinks and land use and fossil and all that stuff. So there does seem to be a plateauing of emissions. Of course, climate change is driven by our cumulative emissions, not our annual emissions. And so a plateauing of emissions just means, all things being equal, a constant contribution of CO2 to warming, the rate of warming. To actually get CO2 to warm the planet less each year, emissions have to decline. And to get CO2 to stop warming the planet, that actually pause global warming, we need to get emissions all the way down to zero. And to reverse global warming, to cool the planet, we need to get emissions below zero. That's kind of the brutal math of climate change, is that, even if we can get the curve all the way down to zero, we're still stuck with all the warming from all the CO2 we've emitted in the past. And if you run a climate model, forward through time, you'll find that once we reach zero emissions, we're stuck with the warming we have for on the timescale of a millennia. There's some uncertainty in what we call the zero emissions commitment, the amount of additional warming or cooling you get after you reach net zero emissions, but it's on the order of 0.3 of a degree plus or minus. There's pretty strong agreement across models that the amount of warming over time, once zero emissions is met, is pretty stable. And the reason for that is because once you get emissions to zero, atmospheric CO2 starts falling, or starts falling actually a bit before you get emissions all the way down to zero. That by itself would cause cooling, but the oceans are pretty far out of equilibrium. You know, again, remember, the deep ocean hasn't warmed at all, really. The surface oceans warmed a ton. And so the oceans are still sucking up more and more and more heat, which again is contributing a bit more to surface warming as the oceans get closer to equilibrium. And so that surface warming effect of ocean heat uptake more or less perfectly counterbalances the cooling effect of falling atmospheric CO2 over time. And so you end up with pretty flat temperatures. And that's a pretty consistent result across models. Yeah.
Clarification, what are the various lines? Say again, please.
So those are just the previous versions of the global carbon budget report. Again, we don't actually know global CO2 emissions perfectly. You know, we're relying on data from countries like China that aren't always great at reporting it accurately, and other indirect measures. And you
I
know,
see, so you're revising history, sort of.
and land use emissions in particular are very uncertain.
Okay.
And so these are just 5 different revisions of historical emissions, with the red being the most recent one, and the most recent one is the error bars, reflecting the uncertainties. So how do these emissions actually break down? We can look at total emissions, which is what I showed in the previous plot. And this is a combination of emissions from fossil fuel and industry, which haven't actually slowed down that much. They've slowed down a little bit compared to what they're doing in the 2000s, but they're still going up at a rate of above 1% a year. And land use emissions, which have actually been falling over the last 15 years, largely associated with reductions in the rate of deforestation in different regions around the world. That being said, land use change emissions are much more uncertain than fossil emissions. And so they were revised very significantly 4 years ago. Previously, we thought they were increasing. Now we think they're falling. Maybe as we get better satellite data and better assumptions in our models, we might have to rethink that. The error bars are big enough that we shouldn't read too much into the decline. But it does turn out that at least our central estimate of flattening emissions is being driven, at least in part, by this apparent decline in land use emissions. Interestingly enough, per capita emissions, you know, the average emissions per person on the planet have actually been declining in terms of total CO2 emissions since the 1960s. So every person is responsible for a little less emissions globally. Now, obviously, there's very big differences across countries. A person in India is responsible for a lot less than a person in America. So this figure is only so useful, but it is noteworthy that, you know, we've already hit peak per capita CO2 emissions. We may have hit peak per capita fossil CO2 emissions. We'll see, it's a little too early to call. But at least on a per person basis, we don't seem to be increasing emissions anymore. And then we can break this down to what's driving these emission changes. So this looks at China, which obviously is a very large increase in CO2 emissions, at least until the last 3 years, when it's been more or less flat. In the last year, it's actually slightly declined, though not enough to really visually see there. The United States, which has reduced its emissions by about 20% so far, but they're still pretty large. The European Union, which has also reduced its emissions by about 20%. India, which has seen a sizable increase in emissions, and then the rest of the world, which is also increasing. This is just fossil fuel emissions, not land use. And then we can also break this down by fuel. About half, or not quite half, but 40 odd percent, 44, I think, percent of emissions is coming from coal, which is the dirtiest fossil fuel. Oil is the next biggest, gas is a smaller wedge, and then there's some emissions from cement and other sources that round up the stack there. And then finally, we can add all this up into a global carbon budget. So this is what I was showing earlier, the fossil fuel and industry and land use emissions. But then where do all these emissions go? Thankfully, they don't all accumulate in the atmosphere. Some do. So the atmosphere takes up a certain amount each year, and that's reflected in the CO2 concentrations in the atmosphere. But the oceans and land also take up a lot of our emissions. About 60%, in fact, of what we emit ends up being taken up by the oceans and land, with the oceans being a little larger than the landscape, but both being pretty substantial. That being said, there has been some evidence recently of a weakening of the landscape, not an absolute weakening. You know, it's still taking up a bit more emissions than it was previously, but a relative weakening compared to what we'd expect it to take up in a world without climate change. There's a piece in Nature that accompanied the Global Carbon Project budget report this year by Pierre Friedlandstein and colleagues that found about a 14 to 20% reduction in the efficacy of the land sink as a result of feedbacks to a warmer world. So essentially, if you model what the land sink would have been if we hadn't had climate change, it would be about 15 to 20% stronger for the same amount of CO2 emissions.
The land sink seems to be very noisy.
It does. And it's strongly related to El Nino and La Nina events, interestingly enough. There's regional fluctuations in rainfall and temperatures that drive vegetation changes.
So it isn't just noise. It's real variation.
It's real variation. I mean, there's some noise, but it's driven by vegetative uptake of different sorts. You know, wildfires can play into that, rainfall patterns, there's a bunch of different factors. But generally speaking, you see bigger lansing during. You see bigger atmospheric growth during El Nino years because you see smaller lansing. So that's why 1988 really big growth in atmospheric CO2, small growth in lansing. 2024 really big growth in atmospheric CO2, small growth in lansing, or small change in lansing. Well, smaller lansing. That's what I'm trying to say. And then there still is a bit of imbalance in this budget. So the dashed line is what you'd expect the sum of all these things to be based on emissions. And so we still don't have a perfect picture of where all the carbon is going. Like there's some periods where there's, a missing sink, some periods where the sink is too big. And so there's more data to collect and more to reconcile there. On a slightly more positive note, as I mentioned, the US and Europe have both reduced their emissions by about 20%. In general, there's about 34 countries now that have seen their carbon emissions peak and decline, even while their economies have grown. These include mostly developed countries, but a couple other interesting ones that are on this list. This is again from the Global Carbon Project. What's interesting is that this result also holds if you account for emissions embodied in trade. It's not just a case of rich countries exporting their emissions to poor countries by, exporting the manufacturing industries out. If you look at emissions embodied in trade, the reductions are a little smaller, but they're still significant in most of these countries. And part of that is that the net emission export from rich countries to poor countries has more or less stabilized over the last 15 years, as in large part China's domestic economy has grown enormously. It used to be a sizable part of China's economy was exports. These days it's like 10%. So it's not enough to affect their emissions all that much. And more broadly, we've moved away from what used to be the worst case scenario. So back in 2011, there were a lot of estimates that suggested that we might be heading toward a world of, 4 degrees or more, that people at the time at least called business as usual, and we'll come back in a moment to what that means. Today, emissions are more flattened out, and it seems like under current policies, our best estimate of warming by the end of the century, at least in my assessment of the literature, is somewhere around 2.6 degrees to 2.9, depends on what estimate you look at. But of course, that's very different from where we want to be. If we want to limit warming to below 2 degrees, with a good chance of being below 2 degrees, we probably need to aim for something like 1.7 or so, like a RCB 2.6 or SSB 1 2.6 scenario, which involves very rapid reductions. That being said, we have moved away from those high emission scenarios, and there's an interesting debate as to exactly why this happens. In particular, there was a scenario called RCB 2.5 that had somewhere between 4 and 5 degrees warming by 2100 that was often referred to in the literature as business as usual, or BAU. Interestingly enough, it was never intended to be business as usual. If you actually look back at the 2011 paper by Radia that developed that scenario, they wrote in that paper that it represented the 90th percentile of baseline no policy scenarios. But as happens sometimes, there's a bit of a game of telephone, and that nuance got lost. And so there was a period there during the 2000s and 2010, or sorry, during the 2010s and early 2020s, when there were many thousands of papers that said under a business as usual scenario, X, Y, and Z will happen. That almost always referred to this high-end scenario, which was more of a worst case scenario. In fact, Glenn Peters and I had a piece in Nature that sort of kicked off a big debate about this that was titled, "We need to stop using the worst case scenario as the most likely outcome." So we're headed today to a fairly different scenario. There's a couple of different drivers to that. We've seen big reductions in clean energy costs, which make some of the assumptions in these high-end scenarios less realistic. So for example, RCP 8.5 and its successor SSP 8.5 had the world using about 5 times more coal than we use today by the end of the 21st century. Global coal use has more or less plateaued over the last decade, and so the idea that we'll be using 5 times more coal in a world of falling clean energy costs seems pretty implausible today, or even 3 times more coal. We've seen more climate policy interventions. Countries have published regulations to subsidize clean energy. Countries like China have undertaken vast industrial strategies to invest and export clean energy technologies. Vehicle electrification has really taken off. A quarter of all cars sold globally last year were electric. Half of all cars sold in China were electric. And in many ways, we've seen the prices of clean energy costs fall faster than expected, and battery costs through technological developments. This has led to a bit of a debate about how much of this apparent success has been driven by policy, technology and how much was due to these scenarios never being particularly realistic in the first place. It's a hard question to fundamentally answer. Like, if you look back at the literature in 2010, most energy modelers expected us to be on a trajectory toward, maybe closer to 4C rather than 5C, but still a significant amount of fossil fuels. Like, the idea that fossil fuels would dominate the 21st century didn't seem that far-fetched at a time where China was building a coal plant every 3 days. And the idea that clean energy technologies would necessarily win on cost was not a foregone conclusion. And I would argue, at least, that policy has played a pretty big role, both directly in subsidizing clean energy, but also indirectly in developing these technologies in the first place, right? Why is solar cheap? Well, US developed it in national labs in the 70s. Germany spent a stupid amount of money deploying it in a place that's not that great for solar in the 2000s that drove down costs significantly because you got economies of scale, you got manufacturing chains, you got assembly line production of panels. And more recently, China has really doubled down on becoming the global exporter of solar to much of the world as a way of creating market dominance. All of these are policy, even if they're not, the type of policy we normally consider of like a carbon tax or, feed-in tariff. Well, Germany was a feed-in tariff, literally, but and so it's really hard to separate out what technology is exogenous, what technology change would have just happened no matter what people did, and what technology is specifically driven by interventions, by policymakers, by allocations of money, by decisions like that. I think it's undeniable that some of the high-end scenarios were never plausible. The world probably would have never burned 5 times more coal regardless, but it could have burned 3 times more coal, could have burned 2 times more coal. There's a lot of different ways to get to 4 degrees warming that were more plausible, that are not plausible today. And so I think it's an interesting debate of how much of this improvement is due to policy and technology versus implausible past assumptions. I also think it's one that's inherently unanswerable because it requires subjective counterfactuals as to what would have happened. But it's worth exploring. And it's important to emphasize that these estimates of current policy outcomes are themselves fairly uncertain. So this is from a paper I published last year where I did a literature review of all of the scenarios in the literature on current policy outcomes, as well as outcomes if countries meet their Paris commitments, and if countries meet their net zero targets, because a lot of countries, most of the world now has adopted, at least on paper, a net zero target. How realistic those are, is the US actually going to get to net zero by 2050? Is China actually going to get to net zero by 2060? I'm skeptical, but if they do, that's what the estimates in literature would give you. And so, the central estimates of current policy scenarios range from, there's one out there here, but, a little bit below 3C to, about 2.4, 2.5 degrees. There's some variation there. But there's large uncertainties associated with each of these. And these uncertainties are associated both with the uncertainty of future emissions, which, we don't know what emissions are going to be over the rest of the 21st century, even assuming current policies stay in place, and uncertainties in the climate response to those emissions. Because even if we knew exactly how much CO2 we're putting in the atmosphere, the Earth system is complicated. Clouds respond in different ways, water vapor responds in different ways, snow and ice responds in different ways. And so depending on the model you pick, you could end up at 2.7 degrees warming for a particular set of emissions, or you could end up at 3.7 degrees warming. This uncertainty in climate sensitivity and carbon cycle feedbacks is really important in assessing what's going to happen, even under a current policy scenario. So, I do think that it's hard to fully rule out warming as much as 4 degrees under current policy scenarios, even if it's become substantially less likely compared to where we were a decade ago, or at least where we thought we were heading a decade ago. Similarly, if we were to achieve our net zero targets in every country that has them today, we'd probably limit warming to below 2 degrees, but, with still pretty good uncertainties. You can't preclude warming 2.5 degrees or even 3 degrees under net zero commitments if we roll 6s on the proverbial climate dice. I think this is the figure that was on the flyer illustrating this talk, but this is a way of summarizing all that data into the range of climate outcomes under current policies, the range of climate outcomes under 2030 NDCs, the Paris commitments, and under net zero commitments. And this is compared to the full range of scenarios in the most recent IPCC report. So I argue at least that we've probably precluded the very high-end scenarios, though it's hard to know for sure. This is a roughly 5th to 95th percentile range, though, as I'll show in a second, it doesn't include some uncertainties like carbon cycle feedbacks, so it should actually be a little bit wider. But we've certainly excluded some of the high end of that range. And we've also probably lost some of the low end of that range. We've wasted too much time, emissions have already occurred. It's not really going to be possible unless countries go well beyond their existing net zero commitments to get much lower than the low end there. But we have seen this very rapid acceleration of clean energy. So this is the amount the world is spending on climate mitigation each year, or specifically on clean energy technologies each year. It includes things like renewable energy, which is in blue here, energy storage, batteries, nuclear, CCS, that tiny little like blue thing, electric vehicles, the big purple thing, electrified heat, which is primarily heat pumps, clean industry, and power grids, mostly transmission. And this has increased pretty rapidly. If you look a decade ago, we were spending about $350 billion a year on the clean energy transition. As of last year, we were spending about $2.1 trillion a year. And to put this in perspective, the amount the world spends on all global militaries combined is about 2.4 trillion. So at this rate, hopefully, if we don't have too many more wars, we'll be spending more on clean energy than we spend on all the world's militaries combined in the next year or two, which I think would be a pretty good milestone to pass. But the climate remains an angry beast, and we're poking it with sticks, to quote Wally Brookford. Even for a particular emission scenario like SSP 2 4.5, there is a wide range of climate outcomes. This is a simulation of 1 million different fair model runs across all of the climate sensitivity and carbon cycle feedback distributions that we used in the AR6. And so for a particular emission scenario, the best estimate is 2.7, I think, for this run. But there is a roughly, 2% chance it's more than 4 degrees warming. A 8.5% chance less than 2 degrees warming. Those uncertainties are really big. And the problem is we're not actually going to know where we're going to end up there until it's too late to change where we're headed. So we should not just plan for the most likely outcome. We should also try to mitigate enough to really reduce the risk of these tail risks to the climate system, because that's where we start seeing these really potentially catastrophic impacts across human and natural systems. I mean, you see pretty bad impacts at 2.6 degrees or 2.7 degrees, don't get me wrong, but 3.5 degrees, 4 degrees warming, that becomes really, really bad. And so the way I like to think about it is that there's really 3 sources of uncertainty when we're going from warming or emissions to warming. So these are if we just had the best estimate for each emission scenario, and these are the old RCP scenarios, we'd end up with those black dots. If you add the uncertainty in climate sensitivity, so how feedbacks respond to changes in temperature, you end up with these uncertainties on top of it. And then if you add in changes in the carbon cycle, so how, good the land and the ocean sinks are and taking up our emissions, you get those uncertainties on top. And those uncertainties, at least for me, are much too wide to be comforting. And even if we've excluded this red scenario, even if we're down in this scenario space here, that's still a pretty big range of warming outcomes that we could have. So I think that's my last slide. So yeah, thanks everyone. I'm happy to spend the last half hour or so just chatting about any of this.
Oh, thank you. Can you handle your own questions?
Yeah.
Yeah, great. Mhm.
What if our CO2 emissions were exactly equal to the amount that's being fixed by the ocean and the land? What happens to the temperature in the long run?
It's a great question. So for a very long time, almost all of our modeling runs implicitly use that assumption. So climate models until 20 years ago, and even some climate models today, don't include biogeochemistry, so they can't go from emissions to atmospheric concentrations. And so for that reason, a lot of climate model experiments just say, what happens if you take 420 parts per million that we have today? Just hold that flat, which is roughly what you get if the sinks and the surface are equal. And so there, what ends up happening is you have that continued ocean heat uptake. And so you end up with another 0.5 degree C warming or so over the next century, maybe a little less than that, it depends on the model. But there is a certain amount of warming in the pipeline under existing CO2 concentrations. Why you don't see that under a net zero scenario is then you have falling CO2 counterbalancing that residual warming.
Yeah, so the oceans will eventually fix enough of the reinforcing to stop continuing.
Yeah, the ocean sinks and the land sinks will keep taking up some of our historical CO2 emissions.
Like forever.
I mean, eventually
Goes into the core of the earth somehow.
Eventually you get silicate weathering and it forms limestone on the bottom of the ocean and subducts. So that's over.
Okay.
But if you look at CO2 So the way you usually model this is you assume a big pulse of CO2. So we emit, I don't know, 1 trillion tons of CO2 overnight. How long does that take to be removed? And it's sort of a series of different steps, like a little more than half of it goes in the first 100 years. And then you get to about 80% removed in the first 70 to 80% in the first 1,000 years, 85% in the first 10,000 years. It's about 400,000 years for full removal of a pulse, because that last 15%, last 10% just has a really long removal time. And you're mostly dealing with silicate weathering and geologic carbon cycle removals at that point. Yeah.
Maybe it's a question for them, will your slides be available?
I can share them after this, yeah. I'm happy to send them out to Sandy. You can share them to me in a year.
Do we have
Yeah.
You kind of alluded to, differences in severity impacts between 2.5 and 4 degrees Celsius. And I gather from the talk that's very focused on climate data, that's not your main area of expertise, but I don't know your familiarity, like you could express, how you ever try to translate these kind of things into costs to policymakers, like how many trillions in damages over a certain time period, or are there researchers who work in that space of kind of?
Yeah, I mean, there's a lot of different estimates up there. Problem is that they vary by an order of magnitude or so, depending on which one you look at. Like, it's a combination of what are the impacts of climate change under those scenarios, which themselves are hard to quantify, and then what is the capacity of society to deal with those impacts. And that itself is very dependent on the underlying socioeconomic pathway we take. So one of the interesting results from the latest generation of scenarios that show socioeconomic pathways is that the most damaging outcome in all those scenarios was not the one with the most warming. It was the one with high levels of warming and high levels of poverty. Because if there's a world where, large parts of the world are still living on close to $1 a day, they're not going to be able to deal with the impacts of climate change at all. I still think that once you start getting into those worlds of 4 degrees plus, it's hard to even extrapolate what that's going to do to a lot of systems because we don't have good analogs. But I am not really an impacts person, so I don't want to go too far ahead of my skis and saying exactly what's going to happen at 3 degrees or 4 degrees or 2 degrees. But there's a lot of good reports in that. I mean, there's a whole working group in the IPCC working group too that's all on that exact question. So.
I do want to ask you an impact question though, since you were
I'll try.
scared you're working on IPCC, but by 2050 in the current scenario, what do you view as the biggest impacts?
By 2050, so there definitely are large changes in heat wave extents. There's large changes in heavy precipitation events that have big implications for things like flooding and increased rainfall associated with severe convective storms. I think wildfires are something that we've started understanding a lot more, and changing wildfire regimes, particularly boreal forests, is quite impactful. And in the Western US, 2050, sea level rise is going to start becoming more problematic. It's probably, that's more of a backlogged one or back-weighted one in terms of its effects. And then, there just are a lot of impacts on the natural world that I don't think we necessarily put as front of mind as we should. Humans are remarkably adaptable. We live in almost every climate on the planet. Ecosystems are not. They don't have technology they can use to adapt, or, we can try, but it usually doesn't work out well when we do. And so there's a lot of species that have very narrow ecological niches, and, a world of 2 degrees warming in 2050 might push a lot of those out of those niches and cause, localized extinctions of a lot of species.
Like corals.
Corals, they're a great example, yes. And most corals are probably gone at 2 degrees warming. Yeah.
We have an online question from David Koo. With the drop of methane reduction policy by the United States, what is the resultant increase in temperature?
So
maybe you should explain what the policy is.
Yeah, so the Biden administration had a set of fairly stringent rules on fugitive methane emissions from oil and gas production. So about half, maybe a little less than half of methane emissions globally are from oil and gas production. And in the US in particular, the production of shale oil is associated with high levels of methane leakage, in part because some of the shale deposits are far from demand for natural gas, and so a lot of it is flared. So the administration had put restrictions on flaring, had required green completions, where you essentially have a pipeline attached as you're opening up the well to capture any outflow of gas. Had required monitoring to make sure there's not any specific pieces of equipment that are leaking a lot. There is an interesting bifurcation where the gas industry in the US is actually quite low emissions. Like you look at places like Pennsylvania that are primarily gas producing regions, they actually have, as far as we could tell, quite low methane emissions by global standards. But the Permian, the Bakken, some of these oil producing fields have quite high emissions. It's probably not enough in a year or two to really register in terms of global temperatures. Again, the US is not that much of the planet, and there's a lot of other methane emissions in agricultural systems and from wetlands and all these other things. In general, there has been a pretty big uptake in atmospheric methane concentrations in recent years. It's still a relatively small contributor to global temperatures compared to the increase in CO2 we've seen over the same period, but it is a worrying sign, and there is some evidence, at least, that that's coming in part from tropical wetlands in a way that might represent more of a feedback to a changing climate rather than a human forcing.
I have a
And
question.
There's another question by Bob Williams. If you scroll up in the chat, you'll see.
Climate-related disasters are effective ways of getting people's attention to the problem of climate change. How close are we to being able to assign the probabilities of different types of disasters, floods, droughts, hurricanes, tornadoes, to global warming?
So we've gotten better at that, but it really depends on what type of disaster you're talking about. So something like tornadoes, I don't think there's much evidence that human warming is playing a role. There's a couple studies that show strong thunderstorms might be becoming more common in some areas that are associated with cyclonic activity, but the connection is very weak. For things like rainfall associated with hurricanes, that's actually something where there has been a lot of work and where we can do pretty good attribution. One of the ways you do that, for example, is that we already have weather models that are quite good at predicting hurricane paths and intensification. You look at ECMWF and it shows you, you're going to have a category 3 here and a category 4 here, and this is how much it's going to intensify. And they're doing all of those dynamical calculations in a weather model based on things like sea surface temperatures and all the other climatic factors. And so you can actually take those exact same models and say, what if sea surface temperatures were 2 degrees cooler? Because that's how much it's historically warmed in that region. How much less rainfall would there be associated with that hurricane? That's relatively straightforward to do with the type of modeling tools we have today. And a lot of the rapid attribution, well, weather attribution and others do of extreme events is driven by those dynamical weather models. So I think for extreme heat events, for heavy precipitation events, in particular, we've become quite good at doing these rapid attribution studies. And that's why we can say that, Hurricane Helene in the devastated Asheville, North Carolina was probably 10 to 15% more rainfall because of climate change compared to a world without climate change. Now, in almost no cases can we say this hurricane was caused by climate change, or without climate change, there wouldn't have been, this heat wave. It's just, we can start to say how much more intense it's become. What was a 1 in 1,000 year event might not be a 1 in 20 year event because of historical warming. And so we've gotten better at making those sort of attribution types. I do think we have to be a little careful because sometimes that nuance gets lost in translation and it becomes Katrina was caused by climate change. And I think we need to be really careful not to make those sort of claims. But in terms of
So a follow-up, if I could.
Yep.
Yeah. So what's the best way then of getting people's attention? Short of saying, hey, it's going to be hotter than you prefer. Is that really the message to send?
I mean, I think extreme events are a useful tool to raise awareness around climate change. I just think we need to be a little careful how we talk about them. And again, like a hurricane having 10% more rainfall can make a really big difference if that's the difference between cresting levee and not.
That wasn't his question. His question was, what is the best way
What is the best
to
way?
warn
Right.
the public?
Yeah.
I knew that. I'd probably have succeeded in warning the public about it more than I have. I mean, I don't know, right? We can talk about the science and the data all we want. We can talk about the impacts that people are having. We can talk about extreme heat. We can talk about a lot of different things. We can talk about what's happening to ecosystems and coral reefs. I think it's hard because it's such a large and all-encompassing issue with so many different facets. It's hard to boil it down into like the sound bites that drive our media ecosystem.
There's another online here. I'm not quite sure if it's a comment or a question from Doreed. On the role of methane generally, not just anthropogenic sources, but permafrost thaws, wetland losses, deep sea hydrates, etc.
Yeah, so methane is the second most important greenhouse gas after CO2. Now, most of the historic warming from methane actually occurred in the early part of the 20th century. If you look at the increase in overall warming effect of methane, that's essentially saying that methane doesn't accumulate in the atmosphere like CO2, so it's more a function of the rate of emissions. But the increase in warming from methane in recent years has been important, but much smaller than that of CO2. If we look at where it's coming from, human emissions from fossil fuels are, of course, important. There's a lot of strong evidence of emissions from wetlands. There's not much evidence to date of meaningful emissions from permafrost, and no evidence that I know of meaningful emissions from clathrates. But those are both areas of concern, particularly permafrost, as we get into warmer conditions where we could have more significant loss.
Some people, especially very techno-optimistic people, I've heard say that it's a solvable problem if we spend enough money. If only we could spend enough money on it, we could solve this problem and go to net zero. You work on a lot of these removal technologies. What do you think? Do you think it is solvable with money?
They even say beyond that, we know what to do.
We know what to do.
We know
Here
what
are
to
the
do.
promising things. You spend trillions of dollars. We can solve it.
I mean, I think if you could spend unlimited money on it, you probably could solve it. I think that we're also not in a world where we can spend unlimited money on it. Like, I think ultimately our ability to mitigate climate change is going to be driven by how much it costs compared to all the other things that policymakers want to do and see as important. I do think there are some areas that we don't know how to solve today. You know, decarbonizing agriculture in particular is a really tough one. You know, and unless you can convince the whole world to go vegan, and good luck doing that. Animal agriculture is going to be a major source of methane and CO2 for the foreseeable future, as well as nitrous oxide from fertilizers. You know, there are ways to produce nitrogen fertilizer with lower emissions. There's are ways to produce synthetic meat in labs. Whether we'll get an uptick of these things, I don't know. You know, there was an estimate recently from the World Bank. They got a lot of criticism where they said, you know, only about half of the technology we need to solve climate change is commercially available today. I think they more recently updated that to only about 60% is commercially available today. But I think it's probably right. Like, there are industrial heat. There's a lot of sectors where we have ideas of what would work. Like, we can come up with things that could solve it, but they're very far from being commercially viable in markets today. And I think there is still a need to work on developing those sort of things. And then on the removal side, you know, that's kind of the last 10% part of the problem, right? There are some emissions that are always going to be too expensive to mitigate, where it might be cheaper to do removals. If we ever want to bring global temperatures back down after overshoot, you need removals. There's some non-CO2 greenhouse gases like nitrous oxide that are probably always going to be there that you need removals to counterbalance. I think it's less of a question of do we need gigatons of removals and more of a question of do we need 3 gigatons of removals or 10 gigatons of removals. And that's a pretty big delta between those if we want to get to net zero. I think in the back you were first.
Yeah, I was curious what you think about, you know, how do you continue this kind of work in the context of kind of an active effort to defund climate science and dismantle kind of climate data repositories and institutions. And, you know, for just a couple examples, like, you know, some Trump with IPCC and the plan to dismantle INCAR. Do you see that as like a bump in the highway and you're gonna kind of recover from that professionally, or is there like gonna be able to participate in the next IPCC as a US citizen? Are you gonna have access to the data you need to make these kind of charts in the future, or where do you see that?
Yeah, I mean, it's definitely worrying. I feel like I'm more insulated than most as someone primarily in the private sector compared to my colleagues at places like NASA and NOAA, who just aren't allowed to talk about climate change anymore. I think there also is a lot of self-censoring going on because people are worried about their career. If they put themselves out there, do something high profile on climate change, they'll get attention from the wrong person in the administration and get fired. How much permanent damage this will cause? I think is a little TBD. I mean, part of it really depends on how much of what the government is trying to do they are legally allowed to do. You know, Congress just essentially ignored the entire administration request to cut NSF funding and NOAA funding and NASA funding and funded everything at current levels. They might try to do what they did with the Department of Education and just say, we're not going to spend that money. I don't know what the Supreme Court will rule, how that's well beyond my area of expertise. But I do think like in a world where funding stays at current levels, a lot of things will mostly carry on until more favorable political climate for climate action. I do think the bigger concern is if this becomes a every 4 or 8 years thing, if we just diametrically switch between caring about climate and rubbishing it as a hoax, it's going to be hard for people to want to take government jobs and stay in them, to get the best scientists working on this in institutions. And it's going to be hard to take any durable action and convince people to like make investments in clean energy or other things if the political winds are so volatile. So I don't know. I think it's not been a great year, but I think so far outside of probational employees, most of the folks working on climate in these organizations are still there. They're just not being as vocal about what they're doing anymore.
I've got a question about the money.
Mhm.
It seems to me that there's plenty of money is allocated to other projects, like the $500 billion they want to add to the nuclear bomb industry. Next cycle. And I think there's a similar problem in other countries trying to control how much goes to weapons versus climate. And do you have any insight into what might trigger a global move to get the actual money that's needed? Or is that a political science question?
I mean, I think it's more of a political science question. What I would say is that the cheaper that alternatives to fossil fuels become, the less political sacrifices needed to move the needle. So if you go back to the Obama administration, for example, you know, solar was 10 times more expensive back then. Wind was 3 times more expensive. Batteries were 10 times more expensive. Like, if you modeled out what it would take to get emissions down significantly in the US during Obama, it was enormous. Today, if you do the same exercise, it's, you know, 70% less money because of the falling cost of these technologies. Well, 70% for mature stuff. There's still other sectors where it's very expensive. But my point being that it's a lot easier to get the political will to move that needle if clean energy gets cheaper. And so I do think that, particularly in a time like this where there's not much political will, a lot of our efforts are best suited toward trying to develop and make lower cost the alternatives to fossil fuels. Because once the political winds swing, once climate is more relevant on the radar of policymakers and, you know, favorable toward the administration or whatever, you know, it'll be a lot easier to justify big action because dollars can go a lot further. But I don't know. It is a political science question.
I have 2 questions.
Mhm.
The first is a mathematical question. When a physicist looks at a curve that is this recent slope is higher than the previous slope, then you think of a second derivative. But then the question is, there are sort of 2 different explanations for that increase in slope, which have profoundly different future implications. One is that there's just been a reset, a one-time reset, like for example, in aerosols. And so we're on a new linear slope, but this linear slope is steeper than the old one, versus a true acceleration, which would have an increase that's going with time squared. And that, I guess, could be explained physically from real feedback events, right? So I think it's good to distinguish between just a different status quo and a one-time delta, you know. And I'd like to know your thoughts about those 2 eventualities.
Yeah, and if it's a one-time delta, it also goes back down to the previous level of warming once aerosol reductions are exhausted, right? You can't go to negative aerosols.
Yeah.
You only get them to 0, and then we're back to the, actually use this. Yeah, once we get rid of aerosols, we're back down to that, right? So I think if all of the acceleration we're seeing in warming is due to aerosols, that would actually be good news.
Good news.
Because it would mean that there's not necessarily a change in the feedbacks that are driving it.
Mhm.
That being said, we don't know. There was a good paper by Helga Gosling in Science back in 2024, where he and colleagues argued that we've seen a pretty significant reduction in low cloud cover over the oceans, about 15% that's persisted for quite some time now. And that reduction in cloud cover, at least in their analysis, could be some combination of 3 different factors. Natural variability, but we don't see anything like that in the satellite record, so there's not strong evidence of it, but we also have a satellite record that only goes back to 1970, so it's hard to fully pull it out. Aerosol changes, we know aerosols are strongly associated with clouds, so reductions in aerosols lead to less clouds, it fits. But the third possibility is that we're seeing less cloud cover because it's getting warmer. And in climate models, one of the single biggest drivers of climate sensitivity, how warm it gets in the future, is what happens with clouds. Climate models that are very sensitive to our emissions have a much stronger reduction in cloud cover than ones that are less sensitive to our emissions. And so when we see this reduction in cloud cover happening in the real world, how much of that is driven by aerosols versus how much is driven by feedbacks is a really important question. Because if it's not all aerosols, if some of that is a cloud cover feedback to warming, then it would be evidence of a higher climate sensitivity.
Mhm.
Yeah. Of this more persistent acceleration.
So-
And as I mentioned, there is a paper in the works right now that argues that only 2/3 of the acceleration is driven by aerosols, which would
That's
then
interesting.
leave some more space for potential feedback changes to explain the rest of the acceleration.
Very interesting. So apropos of this, David Cooley asks again, are the increases in forest fires as climate warms a significant, possibly positive feedback part of the prediction of models?
So they are included in the land modeling for a lot of models today, not all of them. They are also a driver of some recent emissions. The thing with forest fires is that if an area recovers after a decade or 2, it'll restore that carbon, right? The sink builds back up. It's not like fossil fuels where once you burn it, you're not going to reform coal. So it's not as durable an emission source because it comes with a natural sink. But if the regimes fundamentally change, if you get such frequent fires that there's not significant regrowth, or if you cause a switch from like a forest to a savanna type ecosystem because of frequent fires, like there are ways where it can more structurally shift the composition of forests and lead to less full carbon over time.
Well, you were saying last night that actually the albedo could be higher.
Yeah, depending on where the fires
area.
are also matters. If you burn down the whole boreal forest, it would probably cool the planet because you'd have more reflective surface, even with all the extra carbon going into the atmosphere. Let's not do that. But it's an example of how, there are high latitude forests actually probably have a net warming effect, whereas, mid and low latitude and tropical forests have a cooling effect from carbon sequestration.
Geoengineering?
It's too late to talk.
Another
about
talk,
that,
another
but
talk.
I did publish a piece on it in the New York Times back in October, so you can check that out. Cool.
Okay.
Thank
Thank
you,
you.
everyone.
You get back on.
Right.